morning. This is the 14.1 video. This is the introduction to the section on multiple integrals, the chapter on multiple integrals. Last chapter was partial derivatives, and this is kind of this equivalent but an integral. So it's going to be integrating functions of multiple variables. So they have here, this is page 763. They have an overview to the chapter here. It's kind of telling you where we're going in the chapter. We're going to be integrating initially functions of 2 variables and then later functions of 3 variables. And then it shows you some kind of applications of this, volumes, areas of planes, etc. that we'll see with it. And then the first paragraph here in 14.1 is an introduction to the section. So it's just talking about what it was like in Calais and what it's like now. So I'm going to show you in my notes. You can read that paragraph later on your own, or pause it and read it now. But in Calais, what you had was y was a function of x, and you had some interval from a to b. And when you computed the integral, one of the applications of the integral is that it's the area under the curve. If the function is positive, it's the area under the curve. If the function isn't always positive, then it would be net area. But just for simplicity here, I just put area. And what you did was you took the interval from a to b and you divided it up into equal sized pieces, and then you made these rectangles, and these rectangles divided the area up into smaller pieces that you could calculate with length times width, and then that approximated the area under the curve. So that's kind of what it was in Calais. So now in Cal C, you're going to have, instead of an interval from a to b, you're going to have a region R. So in this section, the regions are all rectangles because that makes it easier, because on a rectangle, the bounds are all constants. And so that's sort of how we're going to start, and then we're going to ease into other regions later in sections that come after this one. So what we're going to do, it talks here, we're going to take the region R. And so notice the, in Calais, the interval from A to B, that was just on the x-axis, so it was one-dimensional. Now the region that we're integrating over is 2-dimensional. It's a rectangle, and it's in the xy plane. And so you've got the bounds on the x and the bounds on the y, and that makes this rectangular region in the xy plane. And so each one of those rectangular regions have a width of delta x and a height of delta y. So the area in the xy plane would be the delta x times delta y. And then what you're going to do is you're going to look at the surface. So the surface would be the 3-dimensional surface, the z equals f of x, y. And you're going to look at the piece of that surface that's over your rectangle. So your rectangle, you can kind of think about it like if the sun was directly overhead, that's the shadow. It's down here, so it's the xy plane is where the rectangle is, and then you have the surface above it. And so what it makes are these boxes. See this box here? So the box, the base of the box is a rectangle in the xy plane. And then the height of the box is determined by the function value, which now again would be z's. And so you've got, instead of rectangles, you've got actual boxes. So they're 3-dimensional boxes. So I have it here in my notes. In Cal C, now you're going to have z as a function of x and y. You're going to have bounds on the x and the y, which is going to make your rectangle. And so when you do that, now it's going to be, instead of 2-dimensional area that you're finding, you're going to be finding 3-dimensional volume. And so the volume is going to be, it's the double integral over that region R. The region R, again, here is a rectangle, later can be anything. And then notice here it was dx, 1-dimensional, and now it's dA, 2-dimensional. So you were integrating with respect to x, 1-dimensional, and getting area, which is 2-dimensional. Now you're integrating with respect to area, which is 2-dimensional, and getting volume, which is 3-dimensional. So you're subdividing that volume into boxes that you can again compute the volume of, because volume is just length times width times height, and that's going to approximate the area. So just like in Cal A, the more rectangles you use, the better the approximation. In Cal C, the more boxes you use, the better the approximation. So this doesn't do as good of a job as approximating the volume as this one. So the more boxes you have, obviously, the better. So they talk here on page 764. What these come from, these are double integrals, okay? And this is just one of 2 ways to do it. You can also, this would be x first and then y. You can also do y first and then x. I didn't write it here. But anyway, these would be down here, it would be the limit as the number of these boxes goes to infinity. That's what this volume is. And so, again, I'm not going to read it to you. I'll let you read on your own, but I just sort of highlighted the important stuff here so you can see. So there's some information up here, and then some information here that you can read on your own. And it's just kind of showing the connection between, it talks about it here too, between the Riemann sums from Calais and now kind of how they relate to Calais. So you can look at that on your own later. That's page 764. They also talk, this is just with a specific example, just so you can see before this next theorem. They have this specific example here, this case, and they talk about down here at the bottom of page 765, what happens if you do it in one order, and then on the next page, they talk about what happens if you do it in the other order, and that leads us into this theorem 1 on page 766, which is Beanies Theorem. And it's talking about if the function is continuous, then you can do x first and then y, or you can do y first and then x, and it'll be the same thing. It gives you the same answer if they're continuous. And so it talks more about it here at the bottom of the page, and you can read that on your own. But basically what it's saying is that these are going to give you the same answer. But sometimes one is easier than the other. So when I do it in my notes, on the ones that it lets you set it up yourself, I try to do it both ways to show you that sometimes it's the same and sometimes it's way harder one way. So you can choose which way you want to do it, but keep in mind sometimes one way is a lot easier than the other way. Okay, so here's Beanies Theorem, and write yourself a little note here because you're not going to notice it in 14.1 because all of them are like this, but later you're going to realize this doesn't always work, and it only works when all 4 limits of integration are constants. So the A, B, C, D, they all have to be numbers. If they're not numbers, you can't just arbitrarily switch the order like you can here. And so write yourself a little note somewhere in your notes to remember that, so that later when we get to the cases where you can't switch them, you'll remember when you can and when you can't. Okay, so you can switch them when they're all numbers. All right, so let's look at some examples. The directions in 1 through 12 evaluate the iterated integral, and they talk about that. I forgot to mention it, I showed it to you, but well, I showed you the page it was on. They talk about that here. That's just it's like the double integral equivalent of a definite integral. So it's a definite integral, but it's a double integral, so they call it a repeated or iterated integral. That's all that means. All right, we're going to look at number 2. So for number 2, they already have it set up for us. And so you don't have to do this. I just did it for the first couple of ones just to get you kind of used to it. But notice what you have here. This is what they gave you. So what you want to think about it is, I put these brackets so you can see, you want to do this one first. So you have to work from the inside out. And so on the inside, you're doing this one first, and then you're ignoring this stuff on the outside. So just totally ignore that. So you put your brackets here so you can just focus your attention on this piece. So you are integrating this with respect to y. So just like with partial derivatives, when you do integrals, when you have more than one variable, you have to treat one of them as a variable and the rest of them as constants. So here, if it's dy, I'm treating y as a variable and I'm treating x like a number. So if I ask myself, if this was a number, so let's say it was 2 or something. If this was 2 and I integrated 2 with respect to y, what would I get? Well, I would get 2y. So if I integrate x as a constant with respect to y, I would get xy. Okay? So just treat it like a number. But then because you're integrating with respect to y, you're treating like a variable. So it's going to be 1/2 y squared. And then because you have these numbers to plug in, it's helpful here because see how you have x's and y's? It's helpful here to remind yourself that those are y's because the innermost integral corresponds to the innermost d. So the innermost d is a y, dy. And so the innermost numbers are the y values. So here, just reminding you, you're plugging those in for y, not for x. Okay, so you're plugging those in for y. So you plug in first the top one for y, then the bottom one for y, you're subtracting. And so then here, you're distributing the negative. And then notice you have negative 1/2 and a positive 1/2, so those will cancel. You have x plus x, and it's 2x. And then now notice, now that you're finished with that integral, now this is just a regular Calais integral. So the second integral that you do is just a regular Calais integral. There's only going to be one variable, and you're just integrating it like regular. So that would be x squared, plugging in, simplifies down to 4. Okay, so these are, again, like definite integrals from Calais in that their answer should be a number. So no plus c, and the answer should just be a number. All right, so I'm going to have you try this one on your own. I'll give you the first hint, the first step. Here you want to break these up. And so break it up to x squared over 2 and distribute that negative. So the negative gets distributed, so it's minus y squared over 2. So notice here you're doing x first. So if you're doing x first, x is the variable and y is the number. So this is number, variable, number. Okay, so you can pause it real quick, try this one by yourself, and then come back and see if you got it right. All right, let's look at this. So integrating 1 with respect to x gives me x. And this is the same thing as 1/2 x squared. So it'd be 1/2 times the integral of x squared. And then y squared over 2 is a number. So if it's a number, you just stick an x on it, and it would be that number times x. Okay, now these numbers, see how the innermost numbers correspond to the innermost d, which is an x? So these are x's. So I'm plugging these in now for x. So x equals 0 and x equals 1. Plug in the 1 first and then the 0. Again, just for x. And then, hold on, I'm going to get back to the next page. All right, so it gives me this. Then these were all 0 for the other piece. And it simplifies down to this. And then notice this is just a regular Calais integral. So I do it just like regular Calais. Integrate, plug in, simplify. So 2/3 should have been your answer. All right. So this next one, I kind of just worked out every one in this section that wasn't terrible. So I'm not really going to talk about all of them. I'm only going to talk about the ones that are different. This one is not different. So I'm just going to let you try it by yourself. And then I'll just show you the answer and you can kind of pause it and see. But this one, again, already set up for you. This one, you're doing y first. Okay, so pause the video, try this by yourself, and then come back. All right, so here is the work. The answer should have just been 0. Okay, so you can pause this here and check your work if you didn't get 0, or if you did get 0, good job. Okay, now let's look at one, and this one also isn't anything different. So again, oh, I guess I shouldn't have uncovered it. Let you try it by yourself. Number 8, if you want to try this by yourself, it's very, very important that you can integrate, because pretty much everything from here on out is going to involve integrating. So if you can't integrate, you're going to be messed up for the next 2 chapters and the rest of the semester. So I want you to practice a lot with these. That's why I did so many examples of these. So again, pause the video, try this one by yourself, and then come back and check your answer. All right, so this one's on 2 different pages. So I'll put this, let me tell you the answer first so you know whether or not you need to pause it. The answer is 92/3. So if you didn't get 92/3, here's part of the work. So you can pause it here and check, see if you made any mistakes in this part of the work. And then here's the rest of the work. Okay, so if you didn't get 92/3, you can pause this and see if you can figure out where you went wrong. All right, let's look at one that's different. So number 10, I'm gonna walk through this one because it's a little different. So number 10, they've got it set up for me to do y first. So notice if you're doing y first, I just grouped these together. The x and the e to the x are just a number. So that's just a number. It's just hanging out front because I'm multiplying, and I'm integrating just the y. So the y is 1/2 y squared. These are the bounds on the y because they match up on the insides. And then plug in for y. And you get this. So notice this now is a Calais integral, but it's going to need integration by parts. So you are going to still run across integration by parts and use substitutions very frequently in these problems. So if you need to go back and review that, integration by parts was 8.1. Integration by parts was 8.1. And use substitution, I don't know, into chapter 5, like 5.4, 5.5, 5.6, somewhere around in there is where that was. All right, so this is integration by parts. Again, 8.1 if you need to review it. So you have your u and your dv, and then you take the derivative to get du, the integral to get v, uv minus the integral of v du, and then integrate and plug in. So final answer on that one is 3/2. So again, make sure you know how to do integration by parts and use substitutions because they're still going to come up. All right, number 12. This one, not anything unusual. So again, just for practice, pause the video, try it by yourself, and then I'll show you the work. All right, so hopefully you've tried it by yourself. I'm going to show you the answer first, and then I'll come back and show you the work. The answer should have been 2 pi. So if you didn't get 2 pi, here is the first part of the work. Let's see if you can find your mistake in this. And pause it right here. And then here is the second part of the work. All right, so hopefully you got those right. Now let's move on, and I'm going to start walking through these with you again now. 13 to 20, notice they do not set it up for you. So according to Beanies Theorem, if these are continuous over these regions, then either order works. And so what I've done, you do not have to do this, okay? You just pick one way and just do it one way. But I've done it both ways unless one way was considerably harder than the other, and then I only did the easier way. But just so you can see. So I just call them method 1 and method 2. Don't worry about remembering which is method 1 and method 2 because I just arbitrarily picked one to be 1 and the other to be 2. It doesn't matter. Okay, so this is number 14. And so method 1, I put the x's on the outside and I put the y's on the inside. So you got to match it up. If the y's are on the inside, dy needs to be on the inside. If the x's are on the outside, dx needs to be on the outside. And again, it doesn't matter which one you do first, and you don't have to do them both, but I was just showing you both of them so you can see. And that's probably what I'll do on my solutions is work them out both ways. That way, no matter which way you set it up, you'll be able to check your work. All right, so I'm going to integrate with respect to y first here. So I brought this y squared up and made it y to the negative 2. Add 1 to the power and reciprocal of the new power. Reciprocal of negative 1 is still just negative 1. And then you're plugging in for y. So I put it back in the bottom before I plug in for it. Plugging in, and I get this, which that's like negative 1/2 and a 1, so you can combine them. So it's 1/2, and then that's x to the 1/2. So add 1 to the power, reciprocal of the new power, and I get 8/3. So that's if you do it with respect to y first. And again, you don't have to do this both ways. I'm just doing it both ways to show you, so don't feel like you have to work it out twice. But if you do it with respect to x first, this is with respect to x first. So notice I put the x is on the inside, dx on the inside, y is on the outside, dy on the outside. So I have, I just split these up, and then I rewrote this x to the 1/2 because I'm integrating with respect to x. So it gives me this. This is just a constant, so it's just hanging out. And then I just moved this stuff to the front because that's all a constant. I just plugged in to the x here. So you're taking the square root first, which is 2, and then cubing it, which makes it 8. All right, and then you have this. So now I'm integrating with respect to y, so I bring the y up. And I should get the same answer because it's, according to Beanies Theorem, the same thing. So same answer, 2 different methods. Again, just pick one, don't do them both. But I just wanted you to see. And in this case, both methods were about the same amount of work. Sometimes one is easier, sometimes one is harder. In this case, they are both about the same. All right, so number 18. This one, they are not both the same. So one is considerably easier than the other. And to be able to just tell from looking, that just takes practice. That just takes practicing with a lot of these problems to be able to tell, oh, this setup is going to be easier than that setup. That's the way you can tell. Okay, so here I started with method 1. Method 1, again, doesn't matter which one is which, but for me, I put the x's on the outside, the y's on the inside. So I have the y's here and the y there, the x is here and the x there. So if I'm integrating with respect to y first, notice I have a y down here and a y up here. So this is going to need either integration by parts or u substitution, but because this is y squared, u substitution is going to work. So for my u, I picked the power. And here I just wrote this to remind us what we're taking the derivative with respect to. So because I'm integrating with respect to y, when I do the du, I have to do the derivative with respect to y. So it's whatever variable is here. When you're doing your u sub, that's what you're taking the derivative with respect to. So this is my function. I take the derivative with respect to y, and then I'm solving for dy. And then I'm going to plug that in. And notice the x, y's cancel. So my paper is sticking to my other paper. Okay, so it simplifies down to just this, which I can integrate. And, oh, here we go. Simplifies down to just this, which I can integrate, which is this after I integrate it. They look the same. Don't forget to plug back in for your u. So I put my u back in, and then these are my numbers that I'm plugging in for y. So I plug them in here, simplify, and then it gets me down to this, which is, again, just a basic Calais integral. So I can integrate that like regular. Plugging in. Notice here, e to the 0 is not 0. A lot of people just assume when they plug in 0 that this whole thing's going to be 0, so they just write 0 and ignore it. And that's fine if it's polynomials, because if it's polynomials, yes, when you plug in 0, you're going to get 0. So if you have a polynomial over here, that's totally fine to do that. But if it's not a polynomial, if it's a trig function or exponential function or a log function or something like that, you need to actually show the work where you plug it in, because it's not always going to be 0, and a lot of times it's not. Like here, that's a 1. Okay, so it simplifies down to this. I checked my answer in the back of the book, and they had factored out the 1/2. You don't have to do that, but you can. It's just a personal preference kind of thing. All right, if you tried it with method 2, notice the u substitution is not going to work, because if you do the u being this again, and then you take the derivative with respect to x, the derivative with respect to x is going to be y squared. So this x is not going to cancel out. So a u sub is not going to work with respect to x. So if you were going to do it this way with the x first and then the y, you'd have to do integration by parts. And that's totally fine. If you like integration by parts, by all means, do it that way. But if you don't want to do integration by parts, then just do it the method one way. So I didn't work it out that way just because I would have just done it method one way, because in this case, method one is considerably easier. Okay. So this one, same thing happens, opposite order. Here, I did method one with the y's on the inside and the x's on the outside. This is going to require integration by parts because I've got a y here and a y here, and a u substitution isn't going to work. So that would be integration by parts. So I've decided, forget that. I'm going to try it method 2 and see if that's any better. All right, so method 2, x's are on the inside and y's are on the outside. Notice there does not need integration by parts because there's no x's out here. So if you can't tell what this is going to be, you can do this with a u sub. It should be pretty obvious though, but if you do this with the u sub, the u would be this. Because this is a dx, now when you do the du, you're taking the derivative with respect to x. So the derivative with respect to x now would be y dx, and so the y that's going to end up in the bottom is going to cancel with this y and just leave you with cosine u, which is sine u. Don't forget to plug back in for your u. And then you're evaluating that from 0 to pi. Sine of 0 is just 0, so that piece goes away. So you have sine of pi y. If you need to do that with a u sub, you can, but hopefully you know when there's a number here, it's going to be the reciprocal of that number out front. So since there's a pi here, so 1 over pi here. And then that works out to 2 over pi. All right, so these couple of examples you can see, sometimes one method is way easier than the other method. Hey, I just noticed, I don't know if you can see this, I have a blackberry bush in my yard, and there are some blackberries on it. I need to go pick some blackberries. Do you see my blackberries? Does that make you want to eat a blackberry? I don't really like them, but my husband does, so I need to go out there later and pick those blackberries. How exciting. Okay. 24. This one, I'm going to let you try on your own. So you can pause the video, try it method 1 or method 2, see if one's easier than the other, and then come back and check your answer. All right, so hopefully you have already done this, paused it, tried it yourself. If you did it method 1 with the y's on the inside, so if you did it with the y's on the inside, then this is what you want to look at. Okay, here's my work. My answer should have been 160 over 3. So if you did it with the y's on the inside, you did not get 160 over 3. Here's the first part of the work. You can pause it on this and see if you can find your mistake. And then there's the second part of the work. All right, but if you did it with respect to x first, so if you've got your x's on the inside, you should still get 160 over 3. The answer should be the same, but your work is going to look different. So if you did the x first, then this is what your work should look like. All right, so if you didn't get 160 over 3, you can see if you can figure out where you went wrong. And here, both methods were about the same. All right, so last one, try this one by yourself. Again, you can pick whichever method you want. I'll ruin the surprise and tell you they're both about the same here also. So try this one by yourself. Pause the video. All right, and then now here that's pretty small so you can see both. The answer should be 4. And then here's if you did y first. Here's if you did x first. All right, so that is all from 14.1. 14.1, again, is just the introduction to double integrals. And so notice in 14.2, which is what we're going to do next, it's double integrals over general regions, so they don't have to be rectangles anymore. So it gets a little bit more complicated, and then we go to polar stuff, then we go to cylindrical stuff. So a lot more to go. So it's extremely, extremely important that you understand the 14.1. So after you do the homework, if you don't feel totally comfortable with it, there's a total of 28 problems. I've done most of the even ones for you, which leaves you, I don't know, roughly, what is that, 13 or 14 problems. So you do the hard problems and then go back and do as many as you have to until you feel good about this, because you need to feel good about this. So if you have any questions, send me an email.